AP Pre-Calc, it's Miss Adams again. Lesson 2.7, Day 2, we're going to finish composition of functions. Example 7 starts with three functions, both f, g, and h. They're given as table of value type prompt, and we want to do 2 times the f of g of 2. So let's look at the g of 2. So in the g function all the way over to 2, we got -3. So we have 2 times the f of -3. And in the second piece, we want the h of 0. So at 0, the h of 0 is 3. That gives us 3 times the g of 3. Next, we want to fill in the missing piece for the y value when x is -3 on the f function. When x is -3 on the f of x, our y value is -4. So 2 times the f of -3, and then 3 times the g of 3. So on the g function, when x is 3, on the g of 3, we have 2. 3 times 2. That gives us 2 times -4 and 3 times 2, so -8 plus 6. Our final answer would be -2. Following that process, the g of -2, when x is -2, the g of -2 is -1. So the g of -2 is -1. And then we want the f of g of 2. So when x is 2, on the g of x function, our y value is -3. So we want the f of -3. And then before we multiply, we need the h of -1. So the h of -1 is 1.5. And we need the f of -3. The f of -3 is -4. So 1.5 times -4 would be -6. So these are not too hard. You just have to be careful with them. In part C, if k of x is the absolute value of 3x minus 4, we want to find the values of x where k is the f of g of 0. So what do we know? We know that the f of g of 0 has to be equal to the f of 1, the g of 0, looking back at the table now, the g of 0 is 1. So that has to be the f of 1. And what is the f of 1? That's 4. So knowing what the f of g of 0 is gives us the k of x. And we see the k of x is the absolute value of 3x minus 4. So let's solve that absolute value. 3x minus 4 has to be equal to 4. So two things are true with absolute value. Either 3x minus 4 equals 4, or 3x minus 4 has to be the opposite, so it has to be -4, because absolute value is either a positive value or it's a negative value, the opposite. So 3x minus 4 is 8. 3x minus 4 is 4, so 3x is 8. X could be 8/3. And 3x minus 4 is -4, so adding 4 to both sides, 3x is 0, so x could be 0. That one was a little trickier than the others. For example 8, we want to describe the transformations of the composition of the functions if we're given f of x is x squared, g of x is x minus 1, and h of x is 2x. And remember, we said that the f of g of x and the g of f of x are not always the same. But let's see what happens here. The f of g of x is when y equals the f of x minus 1. So y is going to be, f is x squared, so x minus 1 squared. The f of h of x is when y is equal to the f of 2x. So y is equal to f, which is x squared, with h plugged in, so 2x squared. And then the g of f of x is when y is equal to the g of x squared, and g was x minus 1, and we're going to substitute x squared in there. Okay? So let's look at the graphs of those to talk about the transformations of each one of those. So in the first one, x minus 1 squared is going to take a parabola and shift that parabola 1 unit to the right. So our parabola looks like this. This is a transformation, f of x translated right 1 unit. Because f of x, what was our f of x function? F of x was x squared. So we just picked up the parabola and shifted that parabola 1 unit right. In this one, f of h of x is 2x squared, so that's going to be a very skinny parabola. 1, 2, 3, 4, 5, 6. So it's going to be transformed. It's going to have a shrink factor, or a horizontal dilation, by a factor of a half. So f of x, I'm going to say it's a shrink right now. It's horizontally shrunk closer to the y-axis. Shrink factor is 1/2. And then g of x is squared in this case. So g of x is squared, and it just took the f of x graph and it shifted down 1 unit. Down 1 unit. So we went from here. So just the regular parabola. 1, 2, 3, 4, 5. Okay. So the regular shaped parabola shifted 1 unit down. So using transformations to talk about compositions. Example 9 wants us to look at the graphs and complete the f of x table. So looking at the f of x graph, I'm going to highlight that just a second here. So we can see this is the f of x graph right here. And then that's our yellow graph. And then the g of x graph is in red. That's the g of x. We want the table for each one of those. So f of x going pretty quick. We got -4, -2, 0, 2, 1, 0, 1, 2, and 3. G of x is 2, 1, 0, -1, -2. Let's see, the g of 1, the g of 1, what is that, 1.5, -1.5, -1, -2, and -3. And then the h of x is the composite. So you may need to do a little thinking here. So I want to get rid of that highlighting. So I want to think about this. If we take the g of -4, that's 2, and I want the f of 2, the f of 2 is 1. So this will be a little bit slower. On the next one, the g of -3 is 1. The f of 1 is 0. You see what I'm doing here? Then the g of -2 is 0, and the f of 0 is 1. The g of -1 is -1. The f of -1 is 2. That one just stayed the same. The g of 0 is -2. The f of -2 is 0. And if we continue to work on through that, for the next one you see that the g of 1 is -1.5, and the f of -1.5 looks like it's going to be 1, if that makes sense. The f of g of 1 is the f of -1.5. And if we go to -1.5, it looks like the y value is 1. The g of 2 is -1, and the f of 2, the f of -1 is 2, and then the last two are 0 and -2. So your job is to graph the h of x function on this next piece of graph paper. And hopefully your graph looks like my graph. For example 10, we want for each of the following f of g of x, and g of f of x, and we want the domain of f of g, and then we want to use a graphing calculator to graph each composition and determine whether f of g is equal to g of f. So we're building up to thinking about inverse functions here. F of g of x, f of g of x is f is x cubed minus 1, and we're substituting the cube root of x plus 1. So in this case, when you cube a cube root, you get x plus 1 minus 1, so we have x. This is the domain. The domain of the f of g of x is all reals. Y equals x has the domain of all reals. Then the g of f of x, the g of f of x. So the g of x is the cube root of x plus 1, and we want to substitute where the x is, we want to substitute the f function, which is x cubed minus 1. So x cubed minus 1 plus 1 is the cube root of x cubed, and the cube root of x cubed is x. So here we're seeing the f of g of x and the g of f of x are both equal to x, and their domain is all reals. F of g of x. You see where this is going? And then f of x and g of x on part B, the f of g of x, so our f function is 1/3 x minus 3. We're substituting g in place of the variable. Distributing 1/3, so 1/3 of 3x is x, plus 1 minus 3. We get x minus 2 for our f of g of x. That domain is all reals. And then the g of f of x for part B, g of f of x, g of x is 3x plus 3. We're substituting f, which is 1/3 x minus 3, then distributing 3 times 1/3 and 3 times -3 plus 3. 3 times negative 3 is negative 9. X minus 9 plus 3 is x minus 6. So the g of f of x also has all reals, but they are not inverse functions on part B, where these two, we're looking at the definition for lesson 2.8 on inverses. F and G are inverse functions of each other, but on part B, they are not inverse functions of each other. F and G are not inverse functions. Okay, so we got 2 application problems to finish up the lesson. Let's look at 11 first. We've got the volume in cubic meters of a weather balloon is given by V of R is 4/3 pi r cubed. If the radius is increasing at a rate of r of t equals 1/2 t cubed for positive time in seconds, we want to find the volume as a function of time. So we're given V of R is 4/3 pi r cubed, and we want to substitute the r of t for the r variable. So 4/3 pi r cubed, and we're substituting r of t, which is 1/2 t cubed. So simplifying that, we've got 4/3 pi. So let's see, we can think of this as t to the 9th divided by 2 cubed, 8. So 4/3 pi times t to the 9th divided by 8. 4 divides 8 2 times. So our function v of r of t is going to be pi over 6 t to the 9th, and our units were in cubic meters. So v of r of t is pi over 6 t to the 9th in cubic meters. And last but not least, example 12, the number n of bacteria in a container of leftover food stored in a refrigerator where capital T is the temperature of the food in degrees Celsius can be modeled by this function n of t. When the container is removed from the refrigerator, the temperature capital T of t is 5t plus 3 for the first 3 hours between 0 and 3. Find the composite and explain its meaning in context to the scenario. Now, if this was a question on a free response on the AP exam, you could simplify, you could do the substitution and not have to simplify. So 60 capital T squared, which is 5t plus 3, minus 140 capital T, 5t plus 3, plus 76. That's as far as you would need to go unless they asked you to simplify for a multiple choice question. And if that was the case, then I would use the expand feature on my calculator and simplify that to find 1500 t squared plus 1100 t plus 196, but that's not always necessary on the AP exam. And what does this mean? N of capital T of t, that's going to give us the number of bacteria present, give the number of bacteria that's present in the leftovers when that container has been sitting out for 0 to 3 hours. When it's left sitting on the counter for 0, 2, 3 hours. Then the last example for B, find the number of bacteria present in the food container after the container has been sitting out of refrigeration for 2 hours. So the N of T of 2 is going to be evaluated at 1,500, 2 squared plus 1,100 times 2 plus 196. So the N of the T of 2 is 8,396 bacteria that are present after the food has been sitting outside of the refrigeration. And I use my calculator to do that. I found out that the T of 2 was 13 degrees Celsius. And after 2 hours out of the refrigeration, the T of 13, the N of 13 was 8,396. So that finishes up lesson 2.7. See you for the next lesson.